Okay, once we know about the modulus and the argument of a complex number, we can actually write our the form of a complex number in a different way. Okay, let's go back to that one we had that was 1 plus 3i. That was z. So we had mod z was equal to root 10, and we had the argument of z was equal to 1.25. Okay. Now, let's just draw it again. See what it looks like. It looked something like that. Now, remember what how we initially wrote our complex numbers. We said it was a real part plus an imaginary part. Now let's just bear something in mind here. We know this distance is root 10. We know this distance is 3. We know this distance is 1. And we know this angle is 1.25. Okay? So we can write this as 1 plus 3i. Okay? That's what z is equal to. That's Cartesian form. But another way of doing it is to use a bit of trigonometry. We can say that in the real direction, we are going cosine of 1.25 is equal to how far you go in your real direction over the modulus, over the hypotenuse of that triangle. So the distance you go in the real path is root 10 times cosine of 1.25. Now, how far do we go in the imaginary direction? Would it be the same thing? It's basically this distance here. It would be the sine of 1.25. And remember, all we do to find out a complex number is add the real and imaginary parts. So this complex number can also be expressed as root 10 cosine of 1.25 plus I times root 10 sine of 1.25 radians. Okay? And now I can factor out the root 10, so it will become root 10 becomes cosine of 1.25 plus I sine of 1.25. Okay, so it's a trigonometric way of representing exactly the same thing. Okay, so we can sort of formularize this. Let's just get rid of all of this now. So we can say that any complex number, z equals a plus bi, can be written as z equals the modulus, and I'll call that modulus of z, multiplied by cosine of your angle, your argument, plus I sine of your argument. Okay? So I hope that makes sense. So you know all you need to do to be able to write it in this form is know what the modulus is and what the argument is. And this is what we call polar form. Okay? This one above is Cartesian form. So these are two of the three ways you need to know to be able to express a complex number. Okay? There's a third way that you are going to learn pretty soon. Okay? So again, hope that makes sense. Let me know if it doesn't. But what we're going to do here is we're going to write each of these in polar form. So the first thing I'll always do is I'll do an Argand diagram. And I'm going to do 2i. So here's 2i. So I should be able to clearly see that the modulus is 2. Okay. Mod z is equal to 2. And the argument of z is this angle here, which is 90 degrees, which in radians is pi over 2. So expressing this complex number, 2i is equal to 2 lots of cosine of pi over 2 plus I sine of pi over 2. Okay, they're exactly equivalent. Let's do B. Okay, let's do an Argand diagram. Okay, the complex number looks like this. It's at -3. So we know it has a modulus of 3, not -3. Can't have a negative modulus. And we know that the argument is 180 degrees, that is to say pi radians. So we can say -3 is equal to the modulus, which is 3. That's wrong. Modulus of cosine of pi plus I sine of pi. Okay, they're absolutely equivalent. So we've written it in polar form. Right, last one. Got to do now 1 minus I. 1 minus I. Right, so 1 minus I will be, so 1 in this, so that'll be down here. Okay, 1 minus I. So we know this distance is 1 and this distance is 1. So surely the modulus is going to be root 2. Just a bit of Pythagoras. Okay. Now what we need to know is the argument. Well, the argument is this. It's 270. I mean, I hope you know now that this angle here will be 45 degrees, so that's pi over 4. So it's 2 pi minus pi over 4, which is what? That becomes 8 pi over 4. It's 7 pi over 4. So I know the argument and the modulus, so I can write 1 minus I is the same as its argument, which is root 2, times cosine of, its modulus, which is root 2, times cosine of its argument, 7 pi over 4, plus I sine of its argument. Now, we can actually represent this in a different way, because what we could do is we could take this angle instead. But if I go in a clockwise direction, my angle simply has to become negative. Okay, so I'm going in the wrong direction. So let's just change this a second. We can also say that 1 minus I is, we've got the same modulus. Now this is going to be pi over 4. It's not, it's negative pi over 4. So we're going to say this is cosine of negative pi over 4 plus I sine of negative pi over 4. Now, they are absolutely equivalent. But what we can do is we can make it even better, because we can remember these special identities. Remember that cosine of negative theta is equal to cosine of theta. And sine of negative theta is equal to negative sine theta. I have taught you that in the past, you may not remember, and if you don't believe me, consider the graphs and the transformations of the graphs. They are absolutely equivalent. So another way of rewriting this is that it's equal to the square root of 2, that is identical, minus I sine of pi over 4. Okay, so all three of those would be correct ways of writing the Cartesian complex number 1 minus I. Okay, very, very, very useful stuff. Now, so obviously what I want you to be able to do is convert back into normal form. Okay, so, by the way, one thing I didn't say, sometimes we say in shorthand, if we write this, cosine theta plus I sine theta. Sometimes we write that as cis theta. It's just shorthand, okay? C-I-S theta, okay, cis theta. So what that is specifically saying is write this cosine of 5 pi over 6 plus I sine 5 pi over 6 times the modulus, which is root 3. Okay, we need to write that back into Cartesian form. So again, let's do an Argand diagram. Okay. Now what we know is that the angle is 5 pi over 6. That's nearly pi. So it's maybe somewhere like this, and it has a modulus of root 3. Okay? And what we know is that this angle here is 5 pi over 6, which would suggest that this angle here is pi over 6. Okay? So let's call this x and let's call this y. We can now work out what x and y are. Well, let's just have a look at this a second. So we're going to say the sine of pi over 6 is equal to x over root 3. So x is equal to root 3 times sine pi over 6. So that's sine of 30, that's a half. So x is equal to root 3 over 2. What about y? Well, that's just going to be cosine of pi over 6 is equal to y over root 3. I've done that right. Yes, so it's the adjacent over the hypotenuse. Yeah, okay. So y is equal to root 3 times cosine of pi over 6, which is cos of 30, which is root 3 times root 3 over 2, which is 3 over 2. Okay, that's what y is. So this is 3 over 2, and this is root 3 over 2, this distance here. So I can now see that my complex number has gone, it's gone minus 3 over 2 in the real direction, and it's gone positive root 3 over 2i in the imaginary direction. Okay? So I would hope that you can work both ways. You can turn Cartesian form into polar form, and you can turn polar form into Cartesian form.